Okay, so this is the solution video for 9.2 single slit diffraction. Trying a different format this time. I'm trying to put all the pages onto one slide because then I think I can just zoom to what I need, and then I don't think the video is going to get messed up. Obviously it's illegible as it is, but if I do this, I can zoom in. Naturally, you need to make a sound effect. But here we go with question number 1. Okay, so we start with the first multiple choice question saying that we have wavelength lambda diffracted through a single slit of width x. Intensity of the central maximum of the diffracted light is I naught. Then you double the slit width, and what's the intensity of the central maximum and the angular position of the first minimum? Well, let's address first of all the angular position of the first minimum because that formula is on the data booklet. So the angular position of the first minimum, theta, is lambda over b, where b is the slit width. And so they said that they doubled the slit width. The original slit width was x, and so the new slit width is double that. And so it says, what is the angular position of the first minimum? It's still lambda over b, but b is double x. So the answer to that part would be lambda over 2x. Okay, now for the intensity. The intensity of the central maximum as a function of the slit width, again, as I've said multiple times, to my understanding and to other people I've spoken to about this, other IB physics teachers, it is not actually in the curriculum, and yet here it is within a question. Great. And then the understanding is that as the slit width increases, the intensity of the central slit actually increases with the square of the opening. So if you were to double the slit width, that would be 4 times the intensity, which is an answer choice. And so that would be D. The mark scheme actually says the answer is B. That if you double the slit width, it doubles the intensity. And then I was like looking into it, and so actually someone found the subject report for this exam, which reiterates that the answer is B, but without explanation as to why that's so. This was, I think I told you that that Sokos, the guy who literally wrote our book, actually weighed in on this question and agrees that the answer should in fact be D. So I really don't know what to tell you. I would say I wouldn't get too hung up on that. Again, remember, you need just over half the points to get a perfect 7 out of 7, so just I wouldn't, lose your mind about that. I think the key takeaway is this part right here. Let me change my color, where theta is lambda over 2x, because the formula for angular position of the first minimum is theta is lambda over b. Let's move on to number 2. Okay, number 2, it says single slit. It says that the width of the slit is decreased. What are the changes in the width of the central maximum and the intensity of the central maximum? Of course, the B is the width of the slit. It says that the width of the slit goes down, and then the width of the central maximum is actually the angular width to the center of the first minimum. So if the slit gets smaller, the angle increases, and so the width of the central maximum increases. So it's not going to be decreases, it's going to be A or B. Just to be clear what I'm talking about, I sketched in a very bad sketch of the intensity distribution, but that theta, if this is the center line right here, the theta they're referring to is this angle to where the first minimum is. And so when I say that the angle is increasing, that means that this angle gets bigger. And so from the center of the primary maximum, the central maximum, to its edge, where the first minimum is, that gets bigger. So that would be the width of the central maximum that I'm talking about there. Now, in terms of the intensity, again, here's another question that makes reference to the intensity when supposedly it's not in the curriculum. I guess maybe it's kind of like secretly in the curriculum. And I had to shut the door. My daughter is doing some exercises and is yelling as loud as she can. Um, but anyway, so as the width increases, I mean, it kind of makes sense that as the width increases, that intensity is also going to increase because there's more light coming through. So if there's more light energy coming through, there's going to be the central maximum is going to increase as well. And I think that's I don't know that that's that much of a stretch. It's like, oh, it's not in the curriculum. I think, in terms of kind of physics common sense, it makes sense that if you have a bigger opening, you're going to get more light through. More light that's coming through means that the intensity of what's on the screen is going to be more intense because there are more photons there. So I think that's fair. But at any rate, the width of the central maximum increases and the intensity of the central maximum also increases. Choice A. Wait. Sorry about that. My logic is sound. My answer is not because I explained it badly. Somehow I got my signals crossed. Okay, and yes. So like I said, as the slit width increases, the central maximum will be more intense because more photons are coming through. But that's not what it said. It said that the width of the slit is decreased. So if the width of the slit is decreased, then fewer photons will be coming through, and so the light will be less intense. So the width of the central maximum does increase, but the intensity of the central maximum decreases because fewer photons are coming through a narrower slit. So 2 is B. My bad. At least I caught my mistake. Okay, that's number 2. Let's go to number 3, which I believe is over here. Zoom in. There it is. All right, diagram shows the diffraction pattern for light passing through a single slit. What is wavelength of light divided by the width of slit? So let's actually turn that into variables. Wavelength, of course, is lambda, and we know that the width of the slit is b, and we know that lambda over b is theta, and theta is the angle from the center line here to the first minimum, what they're calling 1, even though I just wrote over it. So let me back that up a little bit. There we go. And then what they're calling 1 is my theta right here. So wavelength over b is equal to theta, which is going to be 1 times 10 to the negative 2 radians, which is and like that's looking at the y-axis, x-axis, I can see that the answer is 1, so the answer would be choice C, because it's 1, right? Wrong, because like I just said, it's 10 to the negative 2 radians. So don't make sure that you don't miss that. I think that's a little bit dirty, but it's 1 times 10 to the negative 2, so in fact, the answer is 1 times 10 to the negative 2, or 0.01 radians. All right, next question. Okay, number 4, monochromatic light of wavelength lambda passes through a single slit with width b produces a diffraction pattern on a screen. Which combination of changes to b and lambda will cause the greatest decrease in the width of the central maximum? So the formula is theta equals lambda over b, and theta, of course, is half the width of the central maximum. Again, sketching that out, that's what theta is. It's the angular displacement from the center line, from the center of the primary maximum to where the first minimum falls. And it says, I want to decrease the width of the central maximum. So decrease the width means that I want my angle to go down. So I can see that the angle and the wavelength, they are directly proportional. And the angle and the slit width, they are inversely proportional. So if I want my angle to go down, I want to have a shorter wavelength and I want to have a larger slit width. So b goes up and lambda goes down, so double the b but half the wavelength, choice C. And here's number 5. Okay, so number 5, we have frequency of light is 500 terahertz, so it's 500 times 10 to the 12 hertz for that frequency. Makes a diffraction pattern out of a single slit. And it says that the angle, the first diffraction minimum, has an angular displacement from the center of 2.4 times 10 to the negative 3 radians. And then it says the frequency is now changed to 750 terahertz. And then they want to know, what is the new angle now? Well, I know that my formula is lambda wavelength over the slit width, but they didn't give us the wavelength, they gave us the frequency. Now we have the same slit, so B, it's going to be the same B for both of them. You can use the information from the frequency and the angle to solve for B, but really we're just kind of like doing a comparison here. So again, since V equals F lambda, we know that to be true, then lambda is V over F. Now I want to solve for B. So B, if theta is lambda over B, then B is lambda over theta. And as so B is lambda over theta, and lambda is v speed over the speed of light over its frequency. So that leaves us with the slit width being the speed of light divided by the frequency times the angular displacement. And so the for the original frequency and theta, the original frequency and angle, that slit width is the same slit width when we change the frequency later. So like the slit width for the original frequency over here, like this original frequency here, once we change the frequency, it's going to be the same slit width. And so we wind up that speed over frequency times theta is equal to before equals speed over frequency times theta after. And we don't actually need the speed, and we actually can get rid of the 1 over. And so basically what we're left with is that frequency times the angular displacement before equals frequency times the angular displacement after. All right, I'm going to erase some of this stuff so I have room to work. And so we have 500 terahertz times 2.4 milliradians is equal to 750 terahertz times theta. So solve for theta. And we wind up with an angle of 0.0016 or 1.6 times 10 to the negative 3 radians. And that would be choice A. All right, there's actually one more multiple choice. I believe it's number 8. But now we're getting into, those were paper 1 questions. Now, like multiple choice, now we're going to start looking at paper 2 questions. Here's 6A, but not all of it is 9.2. So let's jump ahead. In fact, 6A through 6D makes reference to this magnesium fluoride situation, but none of that is... hold on, did I just erase something? No, none of that is 6.2, so I'm not going to need any of that, but I will need 6E, which is it's a different question. I don't know why it's part of question 6, but it then says, light from a point source is incident on the pupil of the eye of an observer. The diameter of the pupil is 2.88 millimeters. And technically, a pupil, even though it doesn't seem like it, a pupil is a single slit. It's not a slit. I mean, it could be for like a cat, but it is one opening, and that is what a single slit is. So that situation right there, light coming into an eyeball, is considered a single slit situation. And so 6E for 2 marks, we're looking at this graph of intensity versus angle. And it's we're basically drawing the intensity graph for a single slit situation. So we're going to give it our best go. So I made an arbitrary marking on the x-axis to show diffraction angle, and I'm going to draw my central maximum, maybe at the maximum intensity. So I'm going to draw a peak that goes all the way up to the top here and then comes back down. And then remembering that the width of the secondary maxima, they have to be half the width of the primary maximum. So what I mean by that, I'm not going to make a secondary maximum that's this wide, right? Because that's the same width as the primary maximum. I do not want that. But instead, the width of the secondary maximum is going to be half the width of the primary. And then you keep on going, getting smaller and smaller and smaller. Do the same for the other side. And it's all like kind of like approximate. Here we go. 6F is a question that deals with resolution, which we'll be talking about very soon, but it doesn't actually have to do with single slit diffraction, so we're going to pass on it for now. So there's 6E, and now we're moving on to 7, which is a double slit question. We are, in fact, going to need 7B to calculate the wavelength of light, but we're going to see why we're going to need that when we actually go to 7D. It says, due to single slit diffraction, the intensity at a point on the screen at a distance of 28 millimeters from M being the center line, or the point that, that the center line connects to. So from there, that point P right there, I'm assuming, they don't make reference to it there. So, they make reference to the point P, kind of right there. But an intensity of 0 means that that is a minimum. So that's kind of like what they're saying. If this was the slit over here, and that's the center line, M being right there, 28 millimeters away. So that would be the center of the first minimum, and so the formula for single slit, that angle is theta over B, will apply. Sorry, the angle is wavelength over B will apply. And so we know what B is. That was given earlier in the problem. It says earlier up here, the width of each slit is increased to 0.03 millimeters. So that's going to be the slit width for our open net's going to be B. And wavelength was actually one of the other questions earlier. Up here, 7B wants you to solve for the wavelength of the light. Now this is kind of dipping back into HESSEL for double slit. We have S equals lambda D over D, where S is the slit width, and so that according to these variables that you're using, this guy right here is actually S, and then D would be the distance to the screen, and then the distance MP, that would be the distance from the center of the primary maximum to the first secondary maximum. That's that right there, MP. So if we bring this back over here, we have S, we have D, and we have D right here, giving us 0.12 times 10 to the negative 3 times 7 times 10 to the negative 3 divided by 1.5. That's going to give me a wavelength of 560 times 10 to the negative 9 meters. And that's the wavelength of our light. The reason why I want to know that is because it's relevant down here in my calculation for theta on 7D. And so that gets me lambda over B being the slit width in this case. That's that 0.03 millimeters that I referred to earlier. And then we wind up with a angular displacement of 0.01867 radians. And we know that the distance to the screen is still 1.5 meters. So I can now do tangent of theta, which is equal to theta for very small angles, equals opposite over adjacent. So basically what I want to prove is that the opposite side does in fact wind up being 28 millimeters. And so when we do 0.0187 times 1.5 from the center line to the first minimum, we wind up with 28 times 10 to the negative 3, or 28 millimeters. So that one was tricky for a number of reasons, but one of them being the fact that you had to go and solve for the wavelength in number 7b first, because they didn't actually give it to us. So a little bit of SL throwback there. Okay, and then they throw in 8. It's another multiple choice, another paper 1. I don't know why this paper 1 snuck in after the paper 2s, but whatever, let's take a look at it. And so we have a single slit. And what's not in the diagram is this angle, theta slash s, and they want to increase theta slash s. Well, I know that theta is lambda over b, where b is the slit width, and lambda is the wavelength. So if I want to increase the angle, I'm going to need to increase wavelength, which is not a choice, or I'm going to need to decrease the slit width. And so decrease width of the slit is choice B, and that's it. And then that number 8 was the last one because 9 makes reference to a double slit, which is not single slit, which is the focus of 9.2. So there weren't a lot of questions in topic 9.2. I thought 7D was there's a lot going on there, but 60, draw the diagram, and then the rest of the stuff, there's a lot of double slit that they kind of pull in with the single slit. But we have our multiple choice questions, and that's pretty much it. I'm annoyed by this number 1, why the mark scheme says B, that although it does not make any sense. D was thoroughly explained to me and to a bunch of us by a few people online, so I don't really know what that's about. And also this notion of how the intensity changes, I still don't think it's in the curriculum, but I think that number 2 is a fair question. Just to be like, oh, there's a bigger slit, the slit width increases, what happens to the intensity of the light? You're letting more light in, so the intensity is going to go up. I don't know, I just kind of think that's common sense. But there you go. So we have these paper 1 questions 1 through 5, and then these paper 2 questions 6E and 7D and 7B by extension. And then number 8 was another paper 1 question. And that's about it. So thank you very much.